we are shifting gears. Not looking at major differences right now, we are going to look at some associations and relationships between some variables. Let's get into it. Alright, we are going to look at some scatterplots, correlation and its attributes. We're going to calculate some correlations, going to see what affects correlations, look at the Spotify Top Tracks of 2000 example. Were all of you even born yet? Coefficient of determination R squared, and some correlation in R. Before we start anything, let's have a quick glance at something. I showed you this a while back when we were looking at different types of data visualizations, but let's look at it again in more depth. Do you think there is a relationship between life expectancy, which is right here on the x-axis, and the amount people spend on healthcare? Do you think that there should be a relationship between that? So if you spend more on healthcare, should you live longer? Do you think there is a relationship there? Looking at the scatter plot, it does look like there is some association between life expectancy and the amount you pay in healthcare. Because look, here, these are the people that live the longest, and if you go up, these are the people that are spending most on healthcare. So it seems like there's some sort of positive relationship. As one goes up, the other goes up. Except, of course, for us, this outlier here, which we need to have a different discussion for that. Correlation. Correlation is a measure of strength and direction of a linear association or relationship between two quantitative variables. It answers the question, how do these two things relate to each other? If one of the variables goes up, what happens to the other one? If one of the variables goes down, what happens to the other one? Now this is the equation for Pearson's correlation. That is just one type of correlation. There are others out there, but we are going to focus on Pearson's correlation. And because it's Pearson's correlation, that means it's time for a historical moment. This lesson's historical moment is brought to you by Karl Pearson. First, some good stuff. Karl Pearson was a biostatistician and a mathematician. He founded the first statistics department at the University College of London. He developed some great statistical tools like the Pearson's product moment correlation that we're going to learn about. But why does there have to be a but? There's been a lot of buts lately. He was a protege of Sir Francis Galton. There they are, just hanging. And as such, he was really into social Darwinism and eugenics. Another one. He had some racist thinking. He said he didn't really believe that people could rise from the lower levels. He was also quoted once as saying, "If the bad stock be raised, the good is lowered." As if it is some sort of zero-sum game that if we help people below us, that we will somehow suffer. So some of our last historical moments have had these but kind of caveats at the end of them. Now, I put it in here because I thought it was important that you also know some of the other parts about them. They did some amazing things that are invaluable to research and to science and to statistics. But they also held these not great beliefs. And this is relatable to our current times too. Think about the last few years where we've started to hear that certain movie executives or music artists or comedians have done something egregious and something wrong by all societal standards, or we hear that somebody holds these terrible racist beliefs. What are we supposed to do with that? Can we still go watch that movie? Can we still enjoy their music? Can we still use their statistical tools? Does it matter? Should it matter? I don't know. I bring all this up because I'm curious what you all think. Should we care? Should we talk about these things? Should these things be mentioned? Should their names even be mentioned? Should we just use their techniques and forget all about the person? Should we forget all about the bad things the person did? Or should we have the whole picture? Which is very difficult because a lot of these people are much older. We don't have lots of accounts like Twitter and Facebook to hold everybody accountable now. So what do we do? How do you feel about this? How do you feel about these situations where we have this amazing stuff that we can use in statistics, but it came because somebody was maybe trying to prove a point that their race was somehow superior? I don't know. Tell me what you think though. I'm really curious. And I know this is uncomfortable, but this is where things happen. Being in this uncomfortable place with your thoughts and figuring out, why is this uncomfortable to me? What do I do with this? These are important things to think about, and I hope you do think about them. Let me know what you think. Okay, back to our regularly scheduled programming. Let's look at some of the main characteristics of correlation. The first is linear trend. Correlations can only handle linear relationships. Next is the direction, whether it is positively or negatively correlated, which we'll talk more about, and the strength. How strong is that relationship or the magnitude of that correlation? Now, I'm only going to tell you that correlation goes between -1 and +1. I just want you to use some of your intuition, some of your gut feelings, get your belly going. And I want you to look at all these, and I want you to try to guess. What do you think the correlation is for each one of these? What do you think the correlation is here? Now, we'll give you this one as a clue. This is a +1 correlation. So, try to figure out the rest, pause me, and then come back. Here are the correlations for these. For the first one, I told you +1. So as this increases by 1, this increases by 1. So it's a perfect 1-to-1 relationship. Now here, we have a negative relationship. So as this number goes up, the y value goes down. So there's an inverse relationship. That is a negative correlation. It's a perfect 1 correlation because it's all perfectly on that line. Here we have 0 correlation. There is no, where would you draw the line here? There's no obvious line. So these two variables are not correlated, whatever they were. In D, we have about a 0.8. So you can see there is a little bit, or quite a bit, of a positive association here. So as x goes up, it looks like y goes up too. Here we have a 0.4, so there is still some relationship, but it's starting to look a bit more scattered when you compare it to this one or this. Not as bad as 0, but getting small. So we have a 0.4 here. Still something going on. It still looks like there's a relationship like right here. So as x goes up, y goes up a little bit too. And lastly, this one is about a 0.7, but negative. So notice, now the relationship is this way. Basically, as x increases, y decreases. So that is a negative correlation. Now here is that correlation scale, like visualized. Now, sort of like with our effect size measures, there is not a strict cutoff for what is considered big or small, but these are some of the conventions. So right in the middle, if your correlation was 0, r equals 0, that's how we denote correlation, there would be nothing going on there. No association, no relationship between the two variables. Then we can either go this way into positive correlation or this way into negative. Now, whether it's positive or negative, the numbers still apply. So if there is a positive or a negative correlation between 0.1 and 0.3, we call that weak. Between 0.4 and 0.6, moderate. 0.7 to 0.8, strong. And a perfect 1, perfect -1, or perfect +1, that is a perfect relationship. So here are some other properties of correlation. They always fall between -1 and +1. The sign of the correlation denotes the direction. So if it's positive, it'll go like this. As one goes up, the other goes up. If it's negative, it'll be like this. As one goes up, the other goes down. Correlation is unitless, meaning that it does not depend on the variable's units. Two variables have the same correlation no matter which is treated as a response variable. This will make more sense in a little bit. I'll explain it further shortly. Correlation is not resistant to outliers. It's kind of like a mean in that way, that if you have one crazy low or one crazy high value, it's going to affect your correlation a lot. Correlation only measures the strength of a linear relationship. It cannot handle, it needs to be a nice straight line. And of course, the mantra that we all have probably heard, correlation does not equal causation. Correlation refers to the degree to which two quantitative, so number variables, are associated. Some other synonyms you might hear are relationship, covariance, dependence, things like that. So here are a few examples of a positive correlation, like your cognitive ability and your grades. So basically, the smarter you are, the better your grades. Not always. There's going to be some people who defy that, but by and large. Maybe self-esteem and job success. So if you have more self-esteem, maybe you're better at your job, or maybe if you're really good at your job, you have more self-esteem. And we have education and income. The more educated you are, the more income you will make. And this negative correlation here. There's maybe a negative correlation between depression and self-esteem. Something important to note is that two correlations have the same correlation regardless of which one you're saying is causing the other one. So let's look at the example between self-esteem and job success. So maybe you have a lot of self-esteem to begin with, and you then are very successful at your job. Or maybe you've become very successful at your job and that has given you a lot of self-esteem. You see how this is maybe bidirectional or cyclic? Not sure. We can't really parse that out in correlation. Same with the correlation between depression and self-esteem. Were there already some self-esteem issues to begin with that then compounded or caused some of that depression? Or does depression lead to having low self-esteem? So this is what's very important, that we don't really assert which one is causing the other one. There are some examples where it's more obvious which one would realistically cause the other one. For example, there is a very high correlation between the clouds we see in the sky and the number of umbrellas you might see out on a given day. Now in that case, is it because we're all carrying umbrellas that we've caused it to be cloudy? No, of course not. We all saw the same stimuli of the clouds and we all brought our umbrellas. Give me a few more examples of positive and negative correlations. I'm curious, what kind of things do you think are associated positively or negatively? Now I'm sure you've heard these two mantras before at some point. The mitochondria is the powerhouse of the cell, which, save that for biology. It's good stuff though. And of course the correlation does not equal causation for the reasons I just mentioned, that we don't know which one is causing which, and there could be other things involved in there that we're just not measuring that are actually causing it. Now I want you to take just a moment and I want you to click on this link. It is hilarious. There are some intensely strong correlations that are completely spurious, meaning that it's all BS. There's actually nothing there, but the numbers look beautiful together. But this is, again, another example of how correlation does not equal causation. Pause the video and go look at some of those. This guy is great. Now let's look at that linear versus nonlinear thing again. We can plot the relationship between two variables. The relationship can either be linear or nonlinear. So these are all linear. They're all just one straight line. These are all nonlinear, and they're represented by one or more curves in the data. There is some prediction you can do with this, but that's a totally different, more advanced technique and way beyond this class. So we have to have these linear relationships to do a correlation. We can calculate a test statistic just like we've been doing to tell us whether the correlation is strong or not. To calculate the Pearson's correlation coefficient, we need a linear relationship between two variables, two quantitative variables, and data for each person on both of those variables. So one person's score on their stress and the number of assignments they have at the end of the semester. For fun, which one of these different scatter plots do you think best captures the relationship for you between your stress level and the number of assignments you have? Which one of these feels like you right now? I'm sure at this point in the semester I'm probably about right there. We got this, everyone. We've got this. Calculate the Pearson correlation. So here is the Pearson's correlation coefficient. It's a lot, so let's break it down. So first here, let's start with this X part. We have one person's score minus the average divided by the standard deviation. Now what does that give you again? That should look familiar. Keep it in mind. We're going to do the same thing over here. And we're going to do this for every single person. So this is person 1 score on stress and person 1 score on the number of assignments they have due. And this is the variance, the standard deviation for their stress and the number of assignments for the entire group. Now we do that for every single person and we sum it as we normally would. And then we're going to divide by our degrees of freedom, the n-1. So what are we doing here? What is this person score minus the average divided by the standard deviation? What was this again? Think back to the beginning of this class. There's z-scores. So you're taking one person and you're taking their stress score, standardizing it. Then you're taking the number of assignments they have, standardizing it. You're going to multiply those two, called cross products. Then we're going to take the sum of all those cross products because we're going to sum them all. So you're going to do this for everybody, transform everybody's scores into z-scores, multiply one person's two scores with each other, sum them all up, divide by your degrees of freedom, n-1. So what's really going on here? We're standardizing everybody's scores on both of the variables, so on stress and the number of assignments. And this is like one person's score. We multiply them together, so your stress score standardized and your assignments standardized. Multiply them. We do that for everybody. We add them all up, and then we divide by our degrees of freedom, and that's how we get a correlation. So let's do an example now. The table below shows the number of hours spent studying and the number of questions correct on a quiz. Compute the Pearson correlation coefficient. So we have some summary statistics here. Great, makes our life easier. But let's also just look at the numbers. I mean, this is a small data set and it's easy to see. If I were to give you a bigger data set, you can't just look at it visually, but we're learning. So let's look at this. We have hours. They're obviously increasing, 0, 2, 3, 4, 5. Then we have number of questions, 2, 3, 6, 9, 10, also increasing. Before we even start, do you think there is a positive or a negative relationship between the number of hours you study and the number of questions you get correct? And is that relationship strong or weak? Do you think it'll be like almost a perfect correlation or kind of scattery and all over the place? Here is a scatter plot. Doesn't look much like one because there's only 5 observations, but it's a scatter plot showing the relationship between the hours studying and the number of questions you get correct. So one person didn't study at all and they got 2 correct. This person studied 3 hours and they got 6 correct, and so on. So here's how we actually calculate the correlation. It's a lot of work and I'm not going to make you do it, but I want you to understand what it means. But this is where it comes from. We're going to take all the scores for the number of hours people studied and we're going to transform them into z-scores. And we're going to do the same for the number of questions, transform everything into z-scores. So now we have all of our z-scores. We are going to multiply both of them. So this person's z-score of number of hours they studied and this person's z-score and the number they got correct, multiply them, and we will have some values here. These are our cross products, and we are going to take the sum of cross products, which is 3.82. That is what all of these added together equals. And we are going to divide by our degrees of freedom, which is n minus 1. We had 5 people, so 5 minus 1 equals 4. So we do 3.82 divided by 4 equals 0.96. What do you think of that correlation? Effects on correlation. What sorts of factors might affect a correlation? Might make it go up or go down? Think about that for a sec. So one thing that can affect a correlation is something known as restricted range. So correlations can be manipulated when the entire range is not fully represented. So how much you zoom in basically matters. So in this example, there is knowledge of geography from grades 1st through 3rd, and it looks like there is nothing going on there. There's no correlation, so it'd be 0. So you would think that it doesn't matter what grade level you're in, your knowledge of geography is not going to go up. But if you actually zoom out and get the rest of the picture, you start to see that there is a linear trend. And it just takes a little while to manifest. Especially if you zoom in, it won't look like there's anything going on there. Another thing that can affect a correlation is outliers. So just like a mean, it can get dragged quite a bit by just one really unwieldy outlier. So extreme values can distort or skew a correlation. Outliers can make a correlation either a lot stronger or a lot weaker, and you always should be checking a scatter plot to make sure that your data clumps kind of normally, not like this zone over here. So notice in this first pane over here, we have a correlation of negative 0.08, so almost 0. Incredibly small, and it's slightly negative, just a little bit. Now, if we add in this one data point, all of a sudden, we have a correlation of 0.85, positive, and 0.85 is pretty strong. So look how sensitive they are to outliers. You got to be careful. Always check your scatter plots. You might be wondering, well, what do you do if you have one of those? It depends. It could just be a miskeyed value, or if it's really a person that got that high of a score, maybe you want to investigate them. It completely depends on the situation and the context. Spotify, top tracks of 2000, before some of you were even born. So I went online and I found this data set. I highly encourage you to go out there and look for data sets because they are out there to be taken and used and analyzed. So I found this one, Spotify top tracks of 2000. There are 2000 tracks in this data file, and it includes things like the year it was released, 2000, the beats per minute, energy, danceability, loudness, liveliness, valence, which is like, is it positive or negative feeling? Does it make you happy or sad? The duration or the length of it, how long the song is, acousticiness, speechiness, and popularity. So of all these variables, which ones do you think will have the highest correlations? Why? Which ones do you think won't be correlated at all? This is a correlation matrix, and I made this using R. Now, one thing you might notice is that there's all these ones right here, and you might be thinking, well, which variables correlate perfectly? That is one variable correlating with itself, which has a perfect one-to-one correlation. So we can ignore the diagonal. Now have a look at this. Which variables have the highest correlations, whether positive or negative? Have a look. Now if you look at all these correlations, we see that energy and loudness have a strong correlation at 0.74. Energy and acousticiness have a moderate to strong correlation, but negative. So the more energy something has, the less acousticy it is. Then we have valence and danceability, and that again means like music that makes you feel like super happy or makes you feel super sad. And I'm assuming here they're coding valence as a positive thing. So the more positive a song is, like, 'cause I'm happy, clap your hands, and all that, makes you want to dance. So 0.51. And then we have acousticiness and loudness. So the louder and more maybe metal something is, the less acousticy it is. So negative correlation of 0.45. And valence and energy. So valence, again, is how happy, sad-ish it makes you. And energy is actually related to like the thrashiness to it. I looked up these variables, and yeah, energy is like most related to like death metal. What is the correlation between loudness and decibels and actual decimal level and energy, a measure of the intensity of something like death metal? It's 0.74. And we can create a scatter plot using a quick function in R that I will show you at the end, that we put energy on the x-axis, loudness on the y-axis, and bam, we have ourselves a correlation that looks pretty strong. Now, in case you're wondering why it's kind of striated like that, it's because R was treating decibels, and the data probably came in such a way, as whole numbers, meaning discrete, and those are integers. So there are no values. None of the songs had a value that was 15.5 decibels, for example. Now we're going to look briefly at some of the variance that is being accounted for and how we can figure that out with correlation. Coefficient of determination, R squared. The coefficient of determination, also called R squared, tells us how much of the variability in one variable, like the questions answered correctly, is explained by the variability in the other variable, the number of hours you studied. So the coefficient of determination is basically saying what proportion of all that variance is explained by the other variable, the number of hours that you studied. All you have to do to get the coefficient of determination is get your R and square it. And 1 minus R squared is the proportion of variance in the response variable that is not explained, even after accounting for the other variable. So how much variability in the sample is explained? R squared. How much of it is not explained? 1 minus R squared. Pretty simple calculations. So now that you know what the coefficient of determination is and what variance is and is not explained, give these two questions a go. Pause me and try them. Number 1. Compute and interpret the coefficient of determination for the number of hours spent studying and the number of questions answered correctly on a quiz. So remember, the correlation was 0.96, so we just square that and we end up with 0.92. Now how do we interpret this? Approximately 92% of the variance, so the differences, in the number of quiz questions answered correctly can be explained by the variance in the number of hours studying. So basically, we can explain some of the differences in people's scores in the number of questions they got correct. We can explain 92% of that based on how many hours they studied for the quiz. In other words, we're saying that people have a different number of questions that they got correct. But how much of that is explained by the number of hours they spent studying? 92% of the differences in people's scores is explained by the number of hours they studied. Number 2, determine the proportion of variance in the number of quiz questions answered correctly that is left unexplained after accounting for the number of hours spent studying. So we already know that our coefficient of determination, R squared, is 92%-ish. So this means that if we take 100 minus 92.16, or 1 minus 0.92, depending on if you want to do proportions or percentages, we end up with 7.84%. That means that 7.84% of the variance in the number of quiz questions answered correctly is left unexplained after accounting for the number of hours studying, perhaps due to some other variables like the person's mood, interest in statistics, or the number of courses that they're taking. 1 minus R squared is basically all the stuff that we do not know. We don't know what else is causing these differences. It's all well and good to tell me how much two variables are correlated, but I want to predict someone's quiz grade based on the number of hours they studied. For this, we will need regression. This is awesome. This is the basis of so much. It's gonna be great. I will see you there. Correlation in R. You can do a correlation in R fairly quickly by just putting in your data. Right here, we have the number of hours and the questions. And all we have to do is say, hey R, give me the correlation. And we say COR, core, the parentheses, and we put our data in there. And we get what we got last time, about 0.96. We can also plot very easily by just saying plot, parentheses, the two different data sets, and here's our little correlation plot. You can also check the significance of a correlation and see if it was just by random chance that you got this strong correlation. We didn't do this in our example by hand, but if you wanted to do it in R, you just say core.test, and bam, here are all of your answers. We have the correlation here, and we have a p-value that is 0.01 something, so it's significant at the 0.05 level, but not at the 0.01. Now here is all the code for the Spotify example I showed you earlier. So we read in the data, Spotify. I'm going to change the duration to numeric. For whatever reason, it was not reading it as numeric, and we need it to be numbers so we can play with it. And we just ask for the correlation for whatever variables we want. Here I did energy and loudness. This is another way to do a plot. It's just a little bit fancier. It's still just plot with the data, but here I'm saying that the main title is this. The X label should be energy and the Y label should be loudness. And lastly, I can ask R to give me the correlation of all the variables using just core and making sure that I tell R to only give me the correlation for the columns that are actually numeric. If you try to do this with columns that are not numeric, like just the artist names, for example, which are characters, it will give you an error and it will not run. So only use numeric or integer columns and variables for that. Here is that plot again. We have energy over here and loudness over here. Then we can get fancy and tell it all the labels, and this is what it looks like. It looks a little bit different from the orange one we saw earlier because I used a fancier package to make that one, which I highly encourage you to go and play with. It's called ggplot2, but it's beyond the scope of this class. And lastly, if you want to make your correlation look fancy like this, so normally R is going to give you a correlation matrix that is completely full, but it's just mirroring all of the information down here. It's kind of redundant. You don't need the second half. So you can run this code here and it'll basically clear out half of it and just make it look a little bit prettier. Not required, but if you ever wanted to do that, that's how you do it. And that's all we got for today's R lesson. See you in the next one. Bye.